So now we'll talk about enable gain surface. So those are your gain scheduling KP, KI, KA, and KG to be scheduled as a function of alpha and V. Practically, this means tuning 88 values. Well, I think here they should say 45 value. Okay, according to the M file, according to here, it's 4 times 9. So it is 45 values, okay, as we saw from previous video. But it looks like they used 88 because they get mixed. They actually took the value of the value from the Simulink 8 times 11, you get 88 values. Okay, so maybe better if you wish to then have 8 value for V and 11 value for alpha, and this is I can simply quickly change it in my code here. Okay, so for alpha I use 11, then according to if I want to consider 88 combination, and for V I have 8 value. Okay, and then I can run my system again. We're having now not 45, 85, if that's the case. Okay, we keep it. Then alright, 88 values in each of the corresponding for loop table. Let's see, did I get the result or what? Attempt to grow array along ambiguous dimension. There is an error. Okay, when I make it growing, it looks like I get an error. But look, V I have it 8 value and 11. So they said the error is in line 13 CT, line 13. Alright, here CT NA times NV, and NA times NV should go this way. Alright, so why you have the error? It is 88. So attempt to grow array along ambiguous dimension. Well, we need to look more closely to understand what's happening. Well, that's V. So alpha V combination should be 88. Well, let me return it back as it is and consider 45 combination. I think must keep it as it is. So here, let's say it is 45. I don't want to take it 88. We may fix the problem later if you wish. But let's continue. Rather than tuning each table entry separately. Okay, so we get the result anyway. Then what we did, parameterize the gains as a two-dimensional gain surfaces. This is very similar to, remember what we did in this problem, chemical reactor. In the chemical reactor, we did something similar. If you remember, we went to here, parameterize the controller gain as a quadratic polynomial in CR. So here linear, multilinear dependence on alpha and V, because here you have two variables. So this is linear, not quadratic, but multilinear, because you have two dependency alpha v, so here alpha times v. So then it means what? It means instead of controlling 88 combination or 45, you have 45 combination, and for each combination you have a gain, assuming for kp. So you want to find 45 kp value and 45 ka and 40. Instead of doing this, this will make or reduce this 45 value to down to only 4, for example for kp. Same for ki, for ka and kg. Good. So then you are reducing it. You are so then computationally more efficient if you use this way. We was doing the same here, right? So we are reducing this approach besides and reducing the number of variable. Well, here it doesn't reduce it too much because you have only one variable, and this CR was, I remember, was five equilibrium point, assuming maybe 9 equilibrium point, I don't remember. But anyway, it's reduced to 3. So for each gain, instead of computing 9 gain, you are computing 3 gain. For 3 gain, yeah. So then you are constructing a surface here, or in the quadratic in the other one. Then we do the same, tuning grid, shape. You see, you do the comparison if you wish. Let's have both together. Okay, and here. Good, you can do this nice comparison. Look at them, very similar. Most gains are initialized to be initially 0, except this one. And if it doesn't work at 0, you put it some value. It doesn't really affect anything. You can put, if they work all 0, you can put them 0. Well, here same, you can put 0 and try, but it is better, it's more efficiently actually to go this way with some good value at the beginning. If you start from a good value at the beginning, so it's more efficiently so the calculation when you do later on SL tuner or systune, later on when you do systune, you will find this is it takes less time. And how to find this value? Basically, what they did, but they have an angle alpha between 0 and 20, so, and they have a v between 700 and 1400. So they said, let's have an average, so it is 10, and an average which is 1050. That's the average of meter per second and degree. And what you do now is a simple linear system control. Very simple now. So what you do, assuming this is my system, or I take this, okay, let's take this one and convert it to one model, one linear dynamic, linearizing it at alpha equal 10 and v equal 1050. Here you did the linearization. But for all the combination of alpha v. So you can take one combination of alpha v and do it as you were doing here. Take one combination and, well, here did they take one combination? Let's see for alpha and v. Initial condition. Well, here they don't take alpha and v. Let's check. because here, yeah, where am I? Sorry, here we have from 1 to 45 combination, and for each combination you take alpha, uh, alpha 0, alpha, etc. So you are taking alpha initial condition. Here you should have some initial condition, and this initial condition must probably are on this Simscape block. If I, they should be here. Okay. If I go to my Simulink block, to that one, or they are working on this, they are not working on this. So let's open it if you wish. Let's open it if you wish. That's the one, just to make sure it is the same that we are using. Maybe it looks like similar to this, but anyway, I will be opening it in different MATLAB workspace. Just, and I'm sure you will have initial condition integrated for alpha and V. So this is V, and where is alpha? The angle in here, where it should be the alpha. And this model, are you sure that's the model we are using? Okay. Maybe they have different notation, but looking at it and do a small comparison with here, alpha is the first one. Okay, so V, Q, A, Z, V. Oh, no, it is not in order, by the way. This is altitude. Okay, this is alpha. This is alpha. Okay, I can see it now. If I go inside here, I see the alpha as internal parameter. Okay, internal parameter that goes here, and imagine you should have some initial condition for it. Well, if you wish, you need to specify input output. Is it all or some input output? Let's see. Of course, they define some input output. I don't want to go over them, but just I will look to the input output. You have input fin deflection, output, EOM3, and selector. Okay, so then this is your output. Quickly looking at it on Simulink, and Q is output, and input is fin deflection. Alright, and now just let's check the initial condition. They should be implemented, so we may see them now, because linearize around initial condition. And now by default, if they are taking the initial condition, model input output, we take model initial condition. If I want to look to the model initial condition, view model initial condition. Okay, you have for position, and let me make it bigger if I can. So you have initial condition for u. In this case, we'll see what's u for theta equals 0. So those are the initial conditions at which you may linearize. Okay, position. We need to see what is position actually by the axis. Okay, theta, u, w, and q. So which one is v actually? You may look. Okay, this is the system I'm working on in this MATLAB. Okay, and here is the definition of things. I find here theta is the incidence angle. So this is actually alpha n in our problem. This, here they give it different name. So the theta is the incidence angle. So here it is 0. So I can put it now 10. Okay, so I can change it later on. Okay, so then this is my state alpha, and for v is related, so it's the speed. We need to see where is the speed. U omega, this is equation of motion. So what is u? So this is the elevator deflection, body altitude. Okay, so body rate u. Those are the initial condition. Input fin deflection. Okay, those are the initial condition you have. Then if I say I want to trim, so I need to follow the guidance, what's known, what's in steady state, etc. Look to the input, deflection, output. Here you go. Output is Q. Again, Q is the body rate. You need to check. It's not the. It's so it is theta dot. I need to check. Okay, body rate not theta dot, because theta for them is the incidence, is alpha. We first need to find the elevator deflection and the resulting trimmed body Q, omega and Q, and then they find this. Well, AZ is for them is an output. Actually, Q and AZ are output. That's what I myself precise. Q and AZ as output. Maybe V here it looks like this. So in this exercise they are not taking V, so that's why we don't see it. Okay, and alpha, it doesn't really appear as alpha. Alpha, it is theta. It is incidence angle, theta, which is some parameter here inside somehow, and we saw it in here in the state. It's one of the state theta. Okay, so that's why we cannot see V. So then I can here change alpha, this theta state. I can give it a different value, it's known, and in here, sorry, not in here, in here, I put the value I want, which is 10 degree, because I said this is equivalent to my alpha, and I need to specify V somehow, if that's what I want for him here. Otherwise, well, so here just to tell, don't go away a lot, just to tell like this parameter, how did we find them? Simply you linearize your system. So this is you do yourself, so I don't talk too much on. You take, if you wish, the simplest way is to cut all, and you take this, and therefore then it turns out this is a better way to go. Okay, this is a better way to go. Let me now check. I'll check in a while quickly, because it looks like this is a better way to go. Q output, and AZ, Q and AZ. Is there any other? We can have all as output, as they did in this exercise. Actually, this exercise, they take all output when they find the transfer function, which is alright. I can take them all. Output, and this is as input. Very nice. Now you do linear analysis. Okay, so then it looks like this is the system which we better go with. You can look to the model initial condition. Again, how this is defined, the internal state, so on. So here clearly we can say, we can look at theta differently. Anyway, and your input is delta. It's called delta. But I'm concerned with alpha and V, and they are output, so that I can find them when I look to the output. So when I do trimming, now I look to the output, I say alpha is known, I put it 10, and V is known, and I put it 150, and I do linearization based on what's considered as known. This is a reactor. What's considered as known and what's unknown, what's in steady state, and what's not in steady state. Okay, so what's known, what's unknown, what's in steady state, what's not steady state, and you put your initial condition. Then you get at the end you will get one. At the end you will get one. So this is the model you work with. You will get equivalent model in which you will build your PID controller. So you will construct on it 3 circuit, 3 loop, as we did as we are doing here. But now, instead of again scheduling, you will simply take PI, P, and P. So, and that will turn out to be a normal controller for one situation, one alpha V situation. Alright, and for it you tune normally your parameter because you have a one linear function, linearized. Alright, so make sure you put the initial condition you want, and then later you can, once you're done, of course not this way, in the other one, once you're done with linearization, you can do analysis, control system tuner, and you tune your your 3 controller, and it turns out you will find something close to this. Okay, or you find different value, it doesn't matter, but this value you put them here as initial condition, and that's what they did themselves. Okay, by the way, as we said before, this is it's impractical to work on it in here. Like if you say output, where is the output? Okay, I want to say, is it for linearization? Because here it's a closed loop, so make sure don't take output as this in case it works, but it's not gonna work. But in case, don't take the output. Say you take output with open loop. So here you need to open the loop if you want to linearize. Then open loop output. Okay, open loop output, etc., etc. Open loop output. If you want to consider this as well, for linearization, why not? You can take them. Okay, then here is your input. But as we said, most probably this is not gonna work in when you do linear analysis. So you see, it is not working. Okay, let's get back to our code here. So now we are doing the comparison between the things here. Well, here it was digitalized, they did digital. So here is similar to here. And then, okay, what else? Block substitution. See, block substitution. Here they use GD, of course. Here they use G. Only they keep it G. And pay attention to the name as we did here. And then your block substitute. Similar. Your register point of interest. We said it's not necessary, but well, you can have them. Like here, it looks like same 1, 2, 3, 4, 5 points. The reference in the middle loop and the reference in the outer loop with its measurement value, and the input, like somehow similar to here. But here you have inner loop and outer loop. Here you have 3 loops, so the first inner loop we didn't take, just to take the middle and an outer loop. But again, this is not needed. Okay. Then you set a block param. Well, you can do it as many, or you can do it just in one single line. And here, once we're done, we need to do the requirement. Here they started by the requirement before. In here, they start requirement. So now they didn't. Now we will go over the requirement in this problem.